I think that is okay. Let's start. So, ah, so hello, Nicholas. Sorry for making you wait. We had a poster session and it's making it very difficult for us to bring them back in. Students are crowded there. 2 minutes.
I see. Yeah, no problem.
Okay, I hope it's okay.
Take your time. I'm not in a hurry, so.
Yeah. So this is the last lecture in the afternoon session, fifth one, and it is. I'm happy to introduce Nicholas Brunner. I have seen him as a young postdoc at Bristol, was working very enthusiastically on the PR boxes, entanglement swapping in PR boxes, and all such things. It's very nice to see him now. He's a professor at uh, University of Geneva, Switzerland, and he is an expert in basically non-locality, steering, and joint measurability, and many more things which you would know. So he's going to talk about Bell non-locality in networks today. So over to you. Yes.
Great.
So you have 30 minutes. If you want, I will remind you. Otherwise,
yes.
Yeah,
Please. I'll try to stick with the time.
Okay, thank you.
Great. So thanks a lot. It was very nice to see you. Also, Usha, we haven't seen each other in many years. So thanks everyone for being here. Let me also thank the organizers for the kind invitation. I'm very sorry I couldn't make it in person, but okay, I'll try to do my best to entertain you remotely for the next half an hour. So as said, the topic of today is Bell non-locality in networks. This is something we've been thinking about quite a bit in Geneva for many years. So here are the main people involved in all the works I'll discuss today. So let me start you with the beginning. Of course, the beginning is Bell non-locality, where so you consider some typical experiment with two distant parties, Alice and Bob, sharing some entangled state and getting some observed distribution, some data. And then the question you ask is whether that data is compatible with the idea of a local hidden variable model, right? So formally, this means can I see my data here, which is the output given input probability distribution? Can I decompose it as a mixture over some hidden variable lambda, right? And then some local response function. So Alice providing an answer A given question X and lambda, and similarly for Bob, right? Now, so what we want to do here is we want to take this question to a new setting, which is that of networks. And so just if we try to sketch a bit the problem, so here is our initial Alice-Bob non-locality setup. And so obviously in a network, we will have many parties. So this is something that people have studied already a long time ago, something called multi-party non-locality, with famous arguments by Mermin and GHZ and so on. And so in this setup, which is quite similar to what people have done in entanglement theory, for example. So you will consider many parties connected by just one source, right? So you can imagine it distributes a very big GHZ state or something like this. And then you study the input-output distribution. Now here we want to do something quite different. We want to take a different approach. And in fact, we want to have a look at a situation like this one here on the right-hand side. So obviously, this looks more like an actual network, at least like those networks that people are trying to build now for future quantum communication systems. And so in this network, well, you see now we have many different sources. Each source produces some bipartite entanglement here. And then we have many parties. But the difference, right, is that each party here is only connected to a small number of sources, right? Now, that may look like a small difference, but actually that's a very big difference, and I'll discuss that quite a bit in detail. So why are we doing this? What is our main hope? Well, our main hope is actually to find something interesting about quantum entanglement, quantum non-locality in this new setup. And in particular, already one point that you can understand at this moment is that there is something new, a new possibility that appears in this network structure, which is the possibility to combine the entanglement of states, right? So here we have many sources producing entangled state, and we can combine that entanglement with the entanglement of measurements. So what do I mean by that? What I mean is the following. Consider this observer here, for example. So you see this observer receives two different quantum subsystems, right? One coming from this source and one coming from that source. And so therefore there is a natural partition at this observer. And so I can now talk about a measurement for that observer being entangled over that partition, right? Which is something I could not do in the standard multi-party non-locality scenario. Okay. Now, just a few statements to start with. So this is, I think, an interesting problem. It's also a quite hard one. And so let me just explain you why by contrasting it to the better known multi-party non-locality case. So when we have one common source, as we have here, well then actually we have a relatively quite good understanding of what's going on. So I'm not claiming that we have solved all problems, but okay, generally speaking, we understand what's going on, and this is because we have adapted methods, okay? So here, everything is convex, and we can deal with linear inequalities and so on, so that's nice and easy. When we go to the network, this is very different because now we have independent sources, so we have nonlinear constraints, everything becomes non-convex, and so here really we are far from having adequate tools. So I'll try to convince you that there are some interesting questions one can ask and that we already made some progress, but I think we're really still very far from having a good understanding and good methods to tackle this problem. So also many opportunities here to make interesting research. Okay, so what I want to do in this talk is I will walk you through this idea of network non-locality. So how do we define such things? What do I mean by locality or classicality in the network setting? Then I'll show you some interesting quantum effects, some nice distributions. And then, if time allows for, I'll discuss something quite new, which we call topological robustness of network non-locality. All right, so let me start with some network. In fact, in this talk, I'll be mostly considering networks with three parties, so quite simple, but you can already see the difference, the main point I want to make. And so let me start with this very simple one here. So I have three parties connected by one source. And as you can see, I'll be focusing here on the situation where I have no inputs. So what does it mean? It means that every party in my network performs a fixed measurement and then provides an output, okay? So in other words, I'm looking at output distributions P of ABC. Right. So now this network here is actually quite boring. I've just put it here to make my main point, which will come in the next slide. But this network here is really, there is nothing interesting. Why? Well, because any distribution you can reproduce classically, right? It's actually enough that you sample here at the source from any desired distribution. And of course, then you can reproduce it, right? So that makes actually my main point is that the network structure is something very important here, right? So let me change that network structure and let me look at this one now, okay? So here you see every pair of parties is connected by a bipartite source. So this is something we call the triangle network, right? So for obvious reasons. Now, how am I going to define locality in this network? Well, I'll do it in a way very similar to Bell, right? So I'll just imagine now that every source produces some classical variable. So I have alpha here, beta, and gamma. And then I will say that an observed output distribution, so PABC here, I'm going to say that it's local, right? Or triangle local, if you want, if it admits a decomposition like this one. Okay, so there are lots of terms, but it's actually quite easy to understand. First of all, we have some distributions of these hidden variables, right? So I have a P alpha, a P beta, and a P gamma. And now you see the important thing is that these factorize, right? So if I want to enforce this network structure, I demand that each of these variables is distributed in an independent way, right? The rest is very similar to Bell, right? Now I look at what each party is doing. For example, Alice. So Alice is providing some output A given variable beta and gamma, right? So I have some response function here, P of A given beta gamma. And then it's the same for the others, right? So this is what I mean when I say that a distribution is triangle local, okay? Now, here comes the first interesting thing is that already in this simple network here, it's possible to witness non-locality. So it's possible to have quantum distributions which cannot be decomposed in this way, right? So this is what we call quantum non-locality without inputs. And so that is quite intriguing from the perspective of non-locality, because usually when you make your Bell inequality test, right, it's crucial that the observers can ask questions, right? And these questions, they are not known in advance to the source that's being tested. Now, in the network picture, right, because you have these independent sources, you can actually forget about these questions, right? It's enough that you always ask the same question. All right, so now I'll try to explain to you two examples of some quantum distributions that are triangle non-local. So here is the first one. It was invented by Tobias Fritz already 13 years ago. And so Fritz had a very clever idea, actually starting from something that we know very well, which is the famous Clauser-Hahn-Shimony-Holt Bell test, right? So the usual Alice-Bob Bell inequality test. And so the idea of Fritz is to embed this one in this triangle. Okay, so I'll explain you how that works. So we imagine that it's actually Alice and Bob here who will play the CHSH game, right? And so to make it interesting, so they share a Bell state, right? This is a 2-qubit Bell state. And now they want to make local Pauli measurements on this Bell state to get some non-local statistics. But of course, you see there is a difficulty here is that, well, for doing the CHSH test, you need some inputs, right? Alice and Bob should ask questions, but here there are no inputs. And so the trick is the following. We are going to use these extra systems here. So this one coming here to Alice and this other one coming to Bob. We are going to use those as some effective inputs. Okay, so we imagine that these sources, they produce classical variables, right? Just a random bit. And so this bit is distributed here to Alice and here to Charlie. And so what Alice is going to do is to look at this random bit, x equals 0 or x equals 1, and then that will tell her which Pauli measurement she has to perform on this qubit particle here, right? So either sigma z or sigma x. Right, and so it's exactly the same on Bob's side, okay? This source generates a y, and so this will tell Bob which measurement he has to do on that particle. Right, so now the first thing is that note that here, these inputs at the moment, they are just effective, right? Because they are distributed by some source. But in general, I don't have access to the information distributed by that source, right? So first thing I need to do is I need Alice to broadcast that information. So Alice will output this X, right? What was her effective input? And so Bob will do the same. You see, Bob will output Y here, okay? Now, in turn, what they are going to do, so X tells Alice which measurement she has to do. She will make that Pauli measurement. And then, of course, she also has to broadcast the result of that measurement that I call alpha. Okay, so this alpha I put here. And so Bob does the same, right? He received Y, and then he gets result beta. And so he broadcasts the input and the output, okay? Now, so far I didn't say anything about this third party here, Charlie, right? So what is the use of this party? In fact, it's crucial that Charlie is there. And the reason here is that Charlie acts as a sort of referee. So Charlie is ensuring that these effective measurement inputs have been distributed in a fair way, right? What do I mean by that? Well, you see, the point is, the problem is having just Alice broadcasting X here, right, doesn't mean that X came from this source, right? X could also have been generated by that source, and that's problematic, right? Because if the source you try to test can choose the questions in your Bell test, well, then you cannot talk about non-locality, right? The input has to come in an independent way, right? So you have to ensure that the X here, this effective input that Alice used, actually comes from this source, okay? And so that's why you use Charlie here, because Charlie will also output X. And so when you verify, right, in the data that the X of Charlie is always equal to the X of Alice, well, then you are guaranteed that it came from that source, right? That's the idea. So if this X is always the same as this one, it cannot come from this source. It must come from this one. And then we use a similar argument for Y, the input of Bob, that is also broadcasted by Charlie. And so if this Y is always equal to this one, then it must have come from this source here, okay? So that's the clever idea of Fritz, right? To embed a CHSH Bell test in the triangle network. And so how do we conclude? Well, then we conclude that if we look at the input-output distribution of Alice and Bob, right? If we look at P alpha beta given XY, as we would do in a normal CHSH test, then if that one is non-local, right? If it violates the CHSH inequality, well, then necessarily my whole distribution, PABC here on the triangle, must be non-local, right? The reason is that if it would not be non-local, then I would have a local model to explain CHSH violation. But of course, that's not possible, right? So that is the argument of Fritz. So that's an absolutely beautiful argument, right, on how to do network non-locality without inputs. But okay, it's a bit disappointing with respect to what I promised in my first slides, right? I told you, we go to networks and we can use entangled states and entangled measurements. But here, okay, I used one entangled state, but obviously there are no entangled measurements, right? And so this is something that motivated people to look for new examples of network non-locality, something that would be, closer to what I want, right? Something with entangled state, entangled measurement, something that has nothing to do with CHSH or any standard Bell inequality, right? So this is an example that we could finally find in 2019 with colleagues in Geneva and ETH. And so here is how it works. Okay, so just qualitatively, in this example, you will see it's very different from the Fritz one. First of all, because now every source here will produce some entangled state. Also, it will be completely symmetrical between exchanging Alice, Bob, and Charlie, right? So there will be no referee, right? Like before, it will be just completely symmetrical. And importantly, we will make use of some measurements which are entangled, okay? Okay, so let me show you how you get that distribution. Well, again, I will use 2-qubit Bell states, right? So each party distributed this psi plus Bell state. And each party makes the same measurement, which is given by these 4 eigenstates here, okay? So you see it's an interesting measurement. Initially, when I told you about an entangled measurement, you may have expected the Bell state measurement, right? That you use in teleportation, for example. But unfortunately, when you use the Bell state measurement, nothing interesting happens. So you need to, to be more imaginative and come up with a measurement like this one here. So this one is quite special. You see it has 2 eigenstates, 0 and 2, that are product. And the other 2 eigenstates, they are entangled, right? But you see that there is some parameter here. There is U and V, right? That allows you to tune the degree of entanglement. All right, so now what's the result? Well, the result is that one can prove that the outcome probability distribution, PABC, for this quantum model here, this one is not triangle local, right? You cannot reproduce it classically. And this is possible, or let's say this is not possible, this is non-classical in this regime here, right? So you see that this parameter U must be in some particular range. In particular, right, the value of 1 over root 2, right, where you would have a Bell state here, this is not included, right? You need to go to weakly entangled states. Right, so now you may wonder, okay, but how do I prove that that distribution is non-local? So that's actually quite an interesting argument. I'll try to explain it. But first, before giving you the argument, let me introduce a new idea, which is token counting. Okay, so now I just forget about my quantum distribution. I go again to a classical scenario here, again in my triangle network. And just imagine that each party distributes a token, okay? And this token can go either left or right. But I'm guaranteed that there is only 1 token per source. Now, what are the parties going to do? Well, they are going to locally count the number of tokens they received and output that number, okay? So this is what I call a token counting strategy, right? This is my model based on this token counting game. Now, obviously, if I have a strategy like this one, my output distribution will have a particular form, right? In particular, because the number of tokens must be conserved, right? There are 3 tokens sent out. No matter where they land, the total amount of tokens should be 3, right? And so, of course, this token counting strategy will always result in a distribution that has the following property, right? That if I sum the outputs A, B, C, I get 3, right? Because of conservation of tokens. So now here is the main thing. This is a rigidity result for token counting. Okay, so what do I mean by that? It means that token counting strategy and distribution is just the same thing, basically. So one way it's pretty obvious. If I have a token counting strategy, as we just seen, then I will get a token counting distribution, right, with that property here. What is much less obvious is that this is also true the other way around. So if I observe a distribution and that it satisfies this token counting property, then I'm guaranteed that the underlying model is of this form here, right? So I'm guaranteed that my strategy is unique. It's a token counting model. So this is something that is reminiscent of self-testing. I've seen that there are a couple of talks about self-testing in the conference. Self-testing is something that we usually associate more to quantum mechanics, right? But actually, in this network structure, self-testing or rigidity is something you can also have classically, right? So here, and this is an example, right? So you have a distribution, And that distribution admits a classical model, but that model is essentially unique, right? There is only that one. So that's actually the main tool that we use for the proof of our quantum distribution. And let me go back to it now. So remember that in my quantum distribution, I had these Bell states. And now if you look at it, this Bell state is a bit like my token, right? This is 0, 1, meaning token goes right, plus 1, 0, meaning the token goes left. But it's a quantum token, right, in a superposition. And then my measurement, right, if I go back to my measurement, this is also a bit like counting the number of tokens. Because I said if the parties receive 0, 0, right, or if they project on 0, 0, this is outcome 0. If they project on 1, 1, this is outcome 2. And then what I'm going to do is that these two outcomes, which are both in some entangled state, I will actually just group them for now. Right? I will coarse grain these two outcomes together. And now if I do that, you see that this is the one token subspace, right? So if I look at this measurement here, I have three possibilities: 0 token, 1 token, or 2 tokens. Okay, so actually you see that my quantum distribution, if I coarse grain it in this way, it becomes token counting, right? Which of course also means that it becomes classical, right? I can do it classically, but the local model is unique, right? Because of this token counting rigidity. Okay, and that is the key step in the proof. Okay, so I take my quantum model, I coarse grain it, and then I say, okay, then here for the coarse grain distribution, there can exist a local model, but that model is unique, right? Now, what do I do? Second step, I go back to the original distribution, right? The quantum one. I split these two eigenstates again, right? And now I can just take my unique classical model and I can check that this one is not compatible with the fine-grained distribution, right? So that's the idea of the proof. You see, it's very clever because, of course, if you have to consider any possible classical model, this is very complicated. There exist infinitely many of these. But because of the rigidity property, you can just focus on one unique model, and then you prove that that model doesn't work. Okay, that's the idea. All right. So now we can actually go one step further. We can even do a quantum self-testing of this distribution. So what do I mean? Now I look at the fine-grained distribution, and actually I go now in the spirit of quantum self-testing, okay? And I can prove that whenever I observe that quantum distribution, then three things must happen, right? So first of all sources must produce some entangled state, right? So I'm guaranteed that in quantum mechanics, the only way to produce this distribution is by having entangled states everywhere, right? I can even lower bound the amount of entanglement. I can also prove that all the measurements must have at least one entangled eigenstate, right? And finally, I can prove, I can certify output randomness. Okay, so I can guarantee that there is a lower bound on the mean entropy here for the outcome C, for example. And that's actually quite interesting because you see, in a sense, it's analogous to device-independent random number generation, so based on Bell inequality test, with the difference that here I no longer need to provide input randomness, right? So in DI random number generation, I always need to have a sort of random seed to choose my measurement settings at random, right? But in the network, because I have no more inputs, then I don't need that, right? This is replaced by the independence condition between the sources. All right. So how am I doing with time? I have 5 more minutes.
Yes, please continue.
Okay. Well, I'll go on for 5 more minutes, then I'll be done. Okay, so let me now discuss something else, which is this idea of topological robustness of non-locality in networks. And so now I want to ask the following question. So suppose I have a big network like the one shown here, but somehow I'm in a scenario where suppose I'm one of these parties here, okay? I sit here, and so I know my neighbors, you know, I know this guy, I know that guy, but what's going on here at the other end of the network, I have no idea, right? This is actually quite a realistic scenario. If you think of the internet, for example, you may know something about the local connectivity, but you know nothing about what's going on, you know, in other continents and so on. So now the question that we ask is, if we are in that setup, right, where we know the local topology, but not the global topology, can we still say something about non-locality, for example? Okay, so we imagine a scenario like this one, where we say, okay, let's put a large part of a network in some sort of cloud, right? We have no idea what's going on there, how the parties are connected. These parties will still announce outputs, right? Like in a bell test. But then, okay, I will have to see if I can prove anything, right? Based only on this model here, right? So meaning that I will just have to consider any possible connectivity here of my parties inside this cloud. Okay, so as you may guess, well, the answer is yes. In a sense, we can do something. We can certify non-locality. So I'll tell you a bit about how that works. So let me look at an example. I'll consider a very large ring networks. Okay, so far we looked at triangles, right? So these are very small rings. Let me now make the ring much, much bigger with n parties. And I will consider the same quantum model as before, right? So everybody here shares Bell states, and each party makes some measurement in the, you know, with this funny measurement with two product and two entangled eigenstates. Okay, so now I get an output distribution, right, over many, many variables here. And that one I can show it's non-local. Okay, it's a bit the same idea as before. Right, now what I want to ask here is the following, right? Now I imagine I put everyone in the cloud except for three people, right? A1, A2, and A3. And so I know the local topology here of these three, right? Here I know nothing. And I witness this output distribution. Okay, then can I say anything about you know, my underlying model? And so the interesting thing is that I can, right? And so I can actually prove that it's non-local. And that I do in the following way. Okay, in fact, it's enough here that I consider the strongest possible model for all these parties here that are inside the cloud. In fact, the worst thing that could happen is that all these parties collaborate, right? And so they all come together in a big box here and they output jointly, right? Now, how do I prove that even in this strategy, I can still certify non-locality? Well, I have to look at the conditional output distributions of A1, A2, A3, conditional on these ones. And so because now I have three here, I'm back to a triangle problem. And so I can prove that this one is non-local in the triangle, right? And that is actually enough to prove that the full distribution is non-local, right? No matter the network topology in this cloud here. And in fact, I can do even more. I can actually even certify a bound on the output randomness of this party here, right? And that bound will actually be independent of which sets of outputs I consider here, right? So in a nutshell, the message is that quantum networks are actually quite powerful in the sense that they will allow you to make non-trivial statements, right, about non-locality or randomness, even in a setting where you know an arbitrarily small part of the network topology, right, while the rest is fully untrusted. So I think that the sort of interesting question one can ask in the network structure, of course, you know, Bell non-locality is always a bit motivated on that black box spirit, right? You want to make it device independent, as people say, right? That you can make statements independently of having a detailed characterization of the devices. And so here you can go a step further, right? Because you can even say something in a scenario where you know almost nothing about the network topology. All right, so let me come to the end. So I hope I could convince you that these are interesting questions, looking at non-locality in this network setting. It's certainly something that's also quite relevant, you know, for experimental developments in where people build quantum networks and so on. These might be interesting tools to certify quantum networks and maybe to develop communication protocols that are interesting. And so I guess in this respect, well, it's crucial to understand what are genuine quantum effects here, and okay, there are also interesting and new things you can find. For example, this topological robustness. Okay, so let me stop here and thank you for your attention.
Let's thank the speaker. So now it is open for questions. Any questions?
Hello, Nicholas. Thanks for nice talk. So in triangle network, you have said that this product measurement, all effector product, that will not give this non-locality. At least one entanglement is required. Am I correct?
Oh, sorry. So your question is it's about the measurement, right?
Yes, measurement. Yeah.
Right. And so you say that the presence of one entangled eigenstate is necessary.
Yes.
Well, actually, no, right? Because if you remember the example of Fritz, right? In the example of Fritz, let me go back to that slide. So you see in the example of Fritz, right? Here there is no entangled measurement, right? You see here what Bob is doing, right, is that he's receiving this input bit here. So this is just a classical bit that he can read. And then based on that bit, he will make a Pauli measurement on that one, right? So I agree. You see, initially I would have agreed with your intuition that, okay, in this network, you need some sort of entangled measurement, but in fact, that's not true, right?
No, but in your one slide, you have shown this triangle things. You said entanglement must be required. Yeah.
Right. So you mean in this one? In this one,
yes.
In this one, so this strategy uses an entangled measurement at each location. But you see, in general, having an entangled measurement is not necessary to get network non-locality without inputs.
No, but for getting genuine network non-locality?
Yeah, if you want it to be, well, okay, it depends what you mean by genuine, okay? But indeed, people have defined, okay, there are different ways in which you could define this genuine network non-locality. And indeed, one would be that you would request to have an entangled measurement. Yes, and so then, of course, it's necessary. Yeah, you're right.
I see. So now I'm trying to think, so let's say this triangle scenario, we go to a square scenario.
Yes.
And all the diagonal also some source is there, means six are there.
Right, like a fully connected network.
Fully connected network, that means each party has 3 qubit.
Yes.
And in that case, if we perform this Bennett shift basis measurement or that things, which doesn't include any entanglement, can it give something genuine in this sense?
Aha, wow, yeah, that's a good question. So for the one you mentioned, I don't know, but I can tell you that.
Explore that question. That is precisely my question.
Yes. So I understand the question. Now for this fully connected graph, and okay, where each party holds 3 qubits, and then you want to do this Bennett et al. Measurement, right?
Yeah, exactly.
That, okay, might give genuine network non-locality. That I don't know. But the one I can tell you for sure is that, you know, Bennett et al., they had another example of some, you know, non-locality without entanglement, which is a 2-qubit measurement.
That is C3, 3-level system we have to take, yeah.
Yeah. And so that is a 2Q trait, right? And so
Yes.
if this one you plug in the entanglement swapping network, okay?
Yeah.
So you have a singlet here, and then in the middle you do this this Bennett et al. Measurement, right?
Yes.
Then you can have genuine network non-locality. Okay, so
Oh,
for that one it works, right? This
I
is
see.
in fact a paper that we wrote with Ivan Supic.
I see. But
For,
qubit, that one is not yet explored.
Sorry?
Qubit, that 4-party, that is not yet explored.
No, the other one that you say is not explored. It's an interesting question. I believe it could work as well, but okay, I don't know for sure.
Okay. Thank you for nice talk.
Thank you.
Yeah. Hello. Yeah, it was a nice talk. So my question is related to towards the last slide, where you are concluding some local nodes using their local structure. They are certifying the network non-locality, right? It is enough. If we get some local structure certifying, then it is enough. So my question is or maybe the understanding is the converse may not be true, right? So the network may be non-local, but not all local structure will be able to certify that. So there may be ABC nodes, they may not certify, but DEF may be able to certify, right? So it's not any local structure is not enough. Only some may be able to, depending on the network. Am I correct?
Yeah, you're right. So for example, if you see, if I would keep only A2 here outside of the cloud, right? If I put A3 and A1 in the cloud, then I cannot prove anything. You're right. So somehow this one here, okay. In fact, to be precise, we have identified two minimal configurations. So this is one here, and it's also possible with having only two, A1 and A2. Okay, so you can put A3 in the cloud, but then that source you should not put in the cloud. Okay, so.
Okay, yeah, so that edge, the edge should not be shared. So there should not be any edge between the cloud and the non-cloud, something like that.
Yeah, so either 3 parties and 2 sources, as we've shown here, right? You see, because in this example, this subsystem and this one, they can come from the same source, right? These ones, they can be joined. So if you have 3 parties, you can do it in this way. If you have only 2, then you have to ensure that in fact this system and that one, they are independent. Okay, so you need to, that's why I'm saying you need to put the sources outside of the cloud. But
okay.
would work as well.
Yeah.
Thanks.
Thank you.
Someone from that side, I think. Oh.
Hello. So, Nicholas, I wanted to ask you one question on, you have tried to look at in the first thing about the CHSH non-locality in the kind of network scenario. If instead, if you had looked at the local hidden state kind of a non-locality, steering kind of a non-locality, you would get different results, right? So like maybe one has to think about the token rigid model of tokens, counting tokens in a different way, condition token or something. I'm not sure, but I wondered the non-localities here and non-localities in the steering scenario would be different. So,
Yes, actually, this is a great question. Okay, I didn't mention it, but look, I'll show you that slide anyway. So here I focused on output distributions, right? So the analog of Bell non-locality, but in networks. Well, of course, you can also ask other questions, right? You can look at other objects. In particular, instead of looking at the output distribution, you could look at the density matrix, right? ABC, like in this one. And so then you have a density matrix, and then you ask whether the density matrix would be network preparable, right? So can you find quantum states here and then local operations unitaries or channel that will produce your state. And then, so as you said, you can also look at something intermediate. So something like steering, right? Where you have some parties that are untrusted, so black boxes, and some that are trusted, right? And then you get the analog of steering. Yeah.
Thank you. So let's thank the speaker. One more. Okay, there is one more question from Manik. So,
thank you.
Yeah, Nicholas, can you hear me?
Yes.
Yeah, this is a little bit more foundational question. I'm trying to understand this source independence assumption in your case.
Yes.
Isn't it very analogous to the preparation independence assumption in PBR theorem?
Aha. Yeah, that's a good question. Yes, indeed.
But
indeed. You see, yeah, sorry.
Why I'm asking this question? Because you see, in PBR's theorem, after PBR's theorem, Arthur Fine put a criticism on this preparation independence assumption.
Yes.
And then Maroni and Leifer come up with another ontology theorem without using preparation independence assumption. So whether something, these kind of things can be done, that even source independence assumption can be relaxed in some sense.
Yes. So I have to say I haven't thought too much about the PBR theorem, but I've thought quite a lot about independence of sources. Also connected to standard Bell tests, right? And so you see, okay, in standard Bell tests, you can also look at relaxed measurement independence, right? Where your inputs can somehow be guessed with some probability by the source, right?
Yeah.
And so, eventually all of these things, they should come in together as one thing, right? In fact, you see the standard Bell scenario, you can also just recast in the network case. And that would also be a network without inputs, a bit similar to this construction of Fritz, actually. And so you see all these things, they should come together in some way, but I have to admit I didn't quite figure it out yet. So it's something we're working on, but we don't yet have really a clear picture.
Okay.
Maybe one thing I can mention. Okay, thanks. You're asking about all my extra slides, but I just mentioned this one. So in this is also something we've considered with Supich and Jean-Daniel Banquel. So going back to this triangle, okay, but now imagine that we want to relax the source independence assumption. Okay, so what we consider is that there is an additional source here, this purple one, and you see this one, it feeds into the three other sources. Okay, so of course, if it can be any causal relation here, but obviously then it becomes trivial again, right? We lose any relevant question here because you can do everything locally. So then what you have to do is you have to limit the independence in some way, right? So you can say that P of alpha, beta, gamma given lambda is, can be almost whatever, right? But maybe they cannot be perfectly correlated. And then you can still show that you can get quantum non-locality, right? Even if these three sources become arbitrarily well correlated.
I see.
But I agree that it's indeed connecting it to PBR is also very interesting. But okay, I have to say that at the moment I don't have really the full picture of what's going on.
Okay, fine. Thank you.
Yeah. Thank you very much.
Hi, Nicholas. So
Hello.
I just want to make a clarification. So
Yeah.
can you go to the last third slide?
This one?
Yeah, this one. So
Yeah.
I wanted to ask, so in this scenario, so you are saying that if there is some triangle non-locality between A1, A2, and A3, then you can say that in the whole network, there is some non-locality.
Yes. So something like this.
if there's so let's say in the other part of the network, I have some non-locality, but here I don't have. Like in A1, A2, A3, there's no non-locality.
Oh, I see. Yeah.
So then you cannot certify, right? In the whole network, whether there is some non-locality or not.
Yeah. Okay. I see. Of course, I went very quickly over this argument, which is not very easy, but let me explain it a bit better. Okay. So the starting point is that, I assume that we are in the honest case, right? So everybody is honest here, right? So we have actually this ring structure, and then we come up with this output distribution, right? Which is a bit the same as we had in the triangle, but now just generalized over a big ring, okay? Yeah. So that's our assumption. We observe that distribution, okay? And that one we can prove is non-local using this token counting again. But now let's imagine that we put all of these ones in the cloud, right? And now we keep only the assumption about the local structure here, right? Now we still observe that distribution, right? Of course, if the parties here announce something else, well, okay, then it doesn't work, right? But suppose they announce, we observe the right output distribution, okay? But we only trust the structure of these three here, okay? And so then the point is that here we can go back to a triangle for the following reason, which is that there exists a combination of outputs A4 to AN here, right? Such that if we post-select on that combination, then the distribution of A1, A2, A3 is non-local one in a triangle.
No, but is it necessary that it has to be non-local in that triangle? That's what I'm asking. So let's say this is...
Well, I don't know if is it necessary? I don't know if it's necessary, but at least for proof, we need it. Yeah, this is how the proof goes. Now, could you... Okay, I see, it's a good question. Could you have something like this, even if that distribution is not? Well, maybe, you see, it might be that there are other sets of outcomes here, such that distribution is local in the triangle. This it might be. I don't know for sure. But at least for our argument to work, you need that there is at least one where it's triangle non-local, right? That's the sort of idea.
Yeah. So if you can't say that this is non-local, then this doesn't follow. That's what I wanted to confirm.
Well, at least the proof how we did it, yeah, wouldn't follow. Yeah, we really need that in the proof.
Yeah. Okay. Thanks.
But you're right. It could, in principle, I guess, in principle, could work even if that's not the case. But okay, then I wouldn't see how to prove it. But I guess in principle it could be. Yeah.
Yeah. Okay.
Well, let's thank the speaker once again, and
thank you
all the speakers in the afternoon session, Professor Devashish, Manik, Joey, and Nicholas, and Arpita. So I thank all of them, and thanks the audience for being very, very interactive. Thank you.
So I think we can thank our chairperson, Professor Usha Devi, and also Devashish Sarkar for the moment. So thank you both. Now I think there is some announcement. No, there is some.
Yeah, so tomorrow we will have a group photo session in the morning, and in the dinner, the cabs will take us to the dinner venue. We request all of you to take all your belongings because the cars will not come back here. They will take the participants to the guest house and the invited speaker to Monotel.
Thank you, Nicholas. So
Yeah,
you are
thank
the
you.
last talk in this session. We are going for a conference dinner. You are welcome.
Ah, yes.